Good afternoon, ladies and gentlemen. I'd like to thank the EU and Thunderbolts Project for inviting me here to speak to you today. Thank you for coming along and listening to what I have to say. Now, the title of my talk is General Relativity, a Case Study in Numerology. Now, I mean that both facetiously and literally, because I'm going to show you today, using mathematics and numbers, that general relativity and all its associated things such as black holes and big bangs are really nothing other than some kind of numerology. And to begin, I'd like to dedicate my talk today to these three late musicians, John Lord from the rock group Deep Purple, and these two men, Huey Thomason Jr. and Billy Jones from the southern rock band, The Outlaws. Some of you, as old as me or older, will certainly remember them. The first thing I'd like to do is to begin by baking a cake. Now, what kind of a cake it is? It is a cosmological cake. The first thing is a bit of a recap before I go into mathematics of all of this, is things that I've spoken of in the past by comparing the characteristics of black hole universes to Big Bang universes and seeing simply the very simple underlying contradictions that make them impossible. Now, the first thing is black hole universes are spatially infinite. There are three types of Big Bang universes, one spatially finite and the other two are spatially infinite, depending on their K curvature values. The black hole universe is eternal. That means it's static. It doesn't depend on time. Whereas Big Bang universes are all finite in age. They're 13.8 billion. I believe that they've now raised it to 13.9 by tweaking a few knobs. Now, the black hole universe is, by definition, something that only contains one mass. Well, that doesn't really correspond to what we see in the sky. I see at least two, and I'm sure you see more than two. Now, Big Bang universes allegedly contain as many masses as you like, and radiation. All black hole universes are not expanding. As I mentioned, they're static. But all Big Bang universes are non-static. All black hole universes are asymptotically flat. Some really esoteric types are asymptotically curved, according to the cosmologists, but we won't be talking about any of them today. They're not worth it. But no Big Bang universe is asymptotically anything. Finally, all black hole universes, or no black hole universes, have a K curvature. And we've already seen that all Big Bang universes have a K curvature, one of three different values. So you see, you cannot put black hole universes into Big Bang universes, or vice versa. But what do the cosmologists do? They mix the two willy-nilly and get millions of black holes, billions of black holes. NASA's found 2.5 billion of them. The ESA just found one a couple of days ago in the Milky Way, not at the center, but revolving with another star. So they've got a binary black hole system. And all of this, of course, in a Big Bang universe. Which one, they don't tell us. They never tell which black hole either, because there are four types, you might recall from a previous talk that I gave. So we'll now move on to baking cake number 2. Black holes have a very schizophrenic property. Right? They have and do not have an escape velocity simultaneously at the same place. Now, no cosmologist understands what escape velocity means. I've mentioned this in detail in my previous talk, but this is a recap today. So that's a problem. Nothing has an escape velocity and no escape velocity simultaneous at the same place. But that's exactly what the black hole event horizon has. In fact, they tell us that the black hole event horizon, the escape velocity or the escape speed of a black hole at the event horizon is the speed of light. That's why nothing can escape. Really? If the speed of light if light is traveling at the speed of light and that's the escape speed, wouldn't you expect light to escape? I would. Let's continue. X is a black hole universe and Y is a Big Bang universe. X plus Y is not a universe. Neither is X plus X or Y plus Y. Why? Because general relativity is a nonlinear theory. You can't just add these together like solutions in simple equations and add them together. You can't do that because it's a nonlinear theory. Here's a simple graphics example of black holes. According to general relativity, or the cosmologist, every black hole has infinite curvature at its singularity. Well, if it has infinite curvature at every singularity, that's gravity. Gravity is not a force in general relativity, it's space-time curvature. So they're telling us that at each one of these black holes, see them in that little drawing there, each one of them has infinite curvature at its center, its so-called singularity. However, Does any one of those have asymptotic flatness? Well, you go from one black hole to another one, and what do you encounter? Infinite gravity. You go from another one to another one, infinite gravity. Every black hole encounters infinite gravity at every other black hole. That's not asymptotically anything, and that violates the definition of a black hole universe. It's supposed to be asymptotically flat at the very least, so it's nonsense. Now we get into a little bit of mathematics. We're up to baking a cake 4.1. Whose cake are we baking? Well, the cosmologist's cake and Einstein's cake, and I think they'd really like to have a file in it somewhere. I'm not going to give them the privilege. Okay, general relativity. Well, these are the equations of Einstein. Now, all you really need to do here is to identify parts. G, what's that? This big G thing? It's Einstein, the Einstein tensor. The R thing there with the arrow there, R sub UV, this is the Ricci tensor. R on its own is derived from the Ricci tensor, and it's called the Ricci scalar. And G, this is an important thing called the metric tensor. It's sometimes called the fundamental tensor. We'll talk about metrics. And lambda is the cosmological constant. And T is the energy momentum tensor. That's it. We've identified all the parts. But what do they mean? Well, the energy momentum tensor is supposed to describe all the material sources of Einstein's gravitational field, and the G is supposed to describe the geometry, because matter causes space-time to curve. So the matter's on the right side, making the space-time geometry on the left side curve. That's gravity, according to Einstein. And the cosmological constant, what is that? Cosmologists don't really know. Einstein didn't really know. It's a fudge factor. Here's an interesting thing. Static and in the absence of matter. According to Einstein, when the energy momentum tensor, which we saw in the previous slide, is 0, his equation is reduced to this thing. The Ricci tensor equals 0. Well, according to Einstein, this describes a gravitational field of a body, or outside a body, such as a star. But this is circular reasoning. First, he removes all matter by setting the energy momentum tensor to 0. There are no material sources. Then, by going in a circle, he comes back and says, this describes a gravitational field outside a body. He just put it back in. Right? Now, some people will object to that. Oh, Crothers doesn't know what he's talking about. He's not on the wrong trial. Well, really, here we can now prove the argument is circular. Because we take de Sitter's universe, it's described by this second equation, R equals lambda G. Well, according to the cosmologists and Einstein, this universe is empty. It's de Sitter's empty universe. Right? It's empty because it doesn't contain anything. Why doesn't it contain anything? Because the energy momentum tensor is 0. Just like the one beforehand. So according to Einstein and his followers, matter is both present and absent by the very same mathematical constraint. Do you think that's possible? I don't. It's not possible. So R, or the Ricci tensor equals 0, that universe, if it's a universe, it's as empty as de Sitter's universe for the very same reason. There are no material sources present. It's a contradiction. So that really bakes Einstein's cake completely. I'll have more to say on this later, because that means that setting the Ricci tensor to 0 is physically meaningless. It has nothing to do with physics. Now we come to a little bit of numerology. This is the so-called Schwarzschild solution, but it's Hilbert's version, and it's a magic trick by Hilbert. In this expression, C equals G equals 1. What's C? It's the speed of light. G is Newton's gravitational constant. And they set them to 1, so they disappear out of the equations. And they claim that this little m in this equation is the mass of the gravity that's the source of the gravitational field that Einstein says Rick equals 0 to. This is the mysterious mass that is taken out and put back in. Let's see how they insinuate Newton into this expression. Let's put C and G in explicitly. Now, Hilbert's expression becomes this. C and G are now present, because if you make C and G 1, we get Hilbert's 2m over r. And notice that they want r to go down to 0. This gives them their two so-called singularities. One, they say they can remove the event horizon of their black hole, because when r is equal to this so-called Schwarzschild radius, they call it a radius, and they give it a value, 2gm over c squared. Again, if g and c are 1, you have r equals 2m. And if you put that into that expression there, you find that the second term with the power to the minus 1 becomes 1 over 0. Right? Well, that's undefined, and they call that the event horizon. Then they put in r equals 0, because they want r to go down to 0. They think it's the radius. And they put in 0, and then the first term gets what? 1 over 0 as well. Now notice, if we rearrange this so-called Schwarzschild equation, or Schwarzschild radius rather, for c, we get c equals the square root of 2gm over r. Well, we recognise that immediately as Newton's expression for escape speed. The thing about this, of course, is that Newton's expression for escape speed pertains to two bodies. You have to have at least two bodies because one escapes from another one. Just because one mass is missing from this equation doesn't mean it's not implicitly present. Because if you have two things, one escapes from the other. And this describes what speed is the necessary minimum for one body to escape from another body when the body that you're referring to has mass m. So by this expression, they have two things: a radius of the event horizon of a black hole, and two, the escape speed of the black hole. That's why they tell you that the escape speed at the event horizon is the speed of light. They got it from Newton's expression. How can you put a two-body relation in what's allegedly a solution to a one-body problem? You can't. Here's some further confusion. This is what I call scientific or delusional science. Right? Delusional science. Cosmologists in confusion. What do they think Hilbert's R is? We saw that expression. I've given a list here. They think it's the areal radius, the coordinate radius, the radius. A guy with a Nobel Prize called Gerardus Tourf tells us this. It's the radius. He tells us also it's the distance, so do many others. He tells us it's the radial coordinate, so do many others. It's the radius of a two-sphere, the reduced circumference, the radial space coordinate. And here's my favourite one of all. A gauge choice, it defines the coordinate R. You know? I could call this Fred Flintstone, or I could call it dark matter, or I could call it doesn't matter. It doesn't matter. Because all of them are wrong. Now we'll come to a little bit of surface theory to see why their mathematics is so false. This is a simple expression. It's called the first fundamental quadratic form for a surface. Now the g's, they're functions of two variables, u and v. U and v are the only variables, and you see here that we have a number of terms, GUU, GUV, GVV. Well, GUV is equal to GVU, so that's why it appears twice. But how many variables are there? Two, because it's a surface. Surfaces have only two variables, two dimensions. The area from Gauss's surface theory is given by, or an element of area is given by the second expression. This is an element of area. You would have to integrate that to get the full area over the range for the domain for values of u and v as required. Now, if u and v are functions of another parameter, we'll call it t. But just because I call it t doesn't mean it's time. I could put in Fred Flintstone. U is a function of Fred Flintstone. I could stick it in there, and then I get now an element of length. Anywhere in the surface, I can calculate length between 2 points in that surface by this parameterized expression. T is the parameter. It doesn't matter what you call it, it's just a dummy variable. Metric tensors. This is a lot of things that cosmologists hide behind. Most of them don't even understand it. They say, oh, well, that's a tensor. Really? What's a tensor? Most of them don't even know that. But they use it nonetheless. Oh, I'll go and read a textbook. The metric tensor. Well, we saw before that we had GUV. Well, we can have G11, G12, G21, G22. That covers the whole four of them. Remember, we had four of them. The first one, the two are in the middle, and the third one, because it's a surface. There are only four components here. And so we can write them together in a matrix like this, and we call this the metric tensor. And the determinant of this metric tensor, well, we just take the determinant. Theory of determinants, we take the determinant of this. It's pretty straightforward. So G will represent the determinant. The GUV, we can write it as a matrix, and we'll call the GUV now the metric tensor. But what's a metric? They sometimes call it a line element. What's a line element? It's nothing other than fancy names for a distance formula. What's the distance between these 2 points? Give me the formula. How do you calculate it? Give me the formula. In elementary algebra or linear analytic geometry, you learn that in, I don't know, year 10. You've got 2 points, x1, y1, x2, y2. What's the difference? The distance between them. You apply the theorem of Pythagoras and you get a distance. Now we do it in little bits. You get a line element. It's a distance formula. That's all it is. So let's have a look particularly at a distance formula. Okay. We want to now calculate a thing called Gaussian curvature, because this will identify what R is in Hilbert's metric. And then we'll see whether or not it can go down to zero. I'm going to show you that it can't go down to zero. And because of that, everything about black holes is immediately destroyed. The intrinsic geometry of a surface is completely independent of any embedding space. So if you take the surface, it's two-dimensional, you stick it in a three-dimensional space, it doesn't matter what kind of space, the intrinsic geometry of the surface is unaltered. In other words, we can talk about the intrinsic geometry of the surface with total disregard to any embedding space. We don't need it. Gauss proved that. Now, in the surface in Hilbert's solution, Hilbert's metric is this one, ds squared. We see there are only two variables, theta and phi. R is not a variable here. There's no dr. R is a fixed quantity. You can assign it some value. Now, if we calculate the Gaussian curvature of a surface, we can do this by using K equals 1 over R1212 over G. G, we saw before, is the determinant of the metric tensor, and R is what? This is a component of the Riemann tensor of the first kind. We won't get into that. All you need to know is that's what it is. And what's G? Well, we see in this case, G11 is what? It's R squared. G1221 is 0 because it doesn't appear. And G22, that's R squared sine squared theta. They're the coefficients of the variables. How do we calculate this? Well, we have to calculate by using we can do it in a number of ways, but here's a simpler way. Now, I'll just go back for a moment. If you look at this metric tensor, you see that you've got R squared in the top left corner and R squared sine squared theta in the right corner. That's a diagonal. If there's zeros everywhere else and not on the diagonal, this is called a diagonal matrix. So we can say that this metric tensor is diagonal. It's mathematical jargon. Now, in the case of tensors that are diagonal, we can use these simple relations to calculate Gaussian curvature. The top equation gives us the Riemann tensor of the second kind, and the second equation tells us how we get from that the Riemann tensor of the first kind, and we want the 1, 2, 1, 2 bit that we saw before. Now, to calculate these other things, these gamma symbols, these are called Riemann-Christoffel symbols, and they're complicated things, but to calculate them, we have these two relations. Now, if you do all of those calculations, the result that we want, the result that we want to concentrate is the bottom one. We get the Gaussian curvature is 1 over R squared. So now we have an identity of what R is in Hilbert's metric. It's none of those things that those cosmologists talk about. R is what? It's related to the Gaussian curvature, and in this case, it's the inverse square root of the Gaussian curvature of the surface. The surface geometry, of course, is independent of any embedding space. So you stick the surface into an embedding space, that's not going to change its identity. What's the real radius in Hilbert's metric? We make a calculation. We integrate the term that contains dr, and then we get this expression by evaluating the constant. I put the constant in, and we get the square root of alpha in the second term. Now, notice something about here. When R equals alpha, and in the case of Hilbert, he assigns alpha to gm over c squared, and then he makes c and g 1. Well, Rp is 0. That's the radius. So that means when R equals alpha, or 2gm over c squared in the case of Hilbert, this equation is 0. The radial distance is 0. So that means that's where the origin of this geometry is located, and there is no possibility for R going less than 0. We look at Minkowski's metric. This is this metric for special relativity, flat space-time. It goes down to R equals 0. We calculate the radius, and we get Rp equals R. They're identical. We go back to the other one. Does Rp equal R there? No, because it's a non-Euclidean geometry. So I calculate the radius, it's a different thing. So in this case, the Gaussian curvature and the radius R are directly related in this form. R is 1 over R squared as a Gaussian curvature, and R is also the radius, because by calculation I get that. Why? Because it's a Euclidean space. The other one is a non-Euclidean space, so they don't have the same relation. So the Gaussian curvature is 1 over R squared. Let's look at Schwarzschild's solution. It looks like Hilbert's. In this case, Schwarzschild's R goes down to 0. But when R equals 0, little r equals 0, what about his big R? His big R equals alpha, the very constant I've been talking about, right? Hilbert's solution is therefore not equivalent to Schwarzschild's, because if it was, that would make Schwarzschild's big R have to go down to minus alpha, but it can't. It's defined in terms of R greater than or equal to 0. Let's have a look at Droster's solution. This looks exactly like Hilbert's solution, except it's got an alpha rather than 2m. And alpha is less than or equal to R. Again, here C is 1. And we'll have a comparison with Brillouin's solution. Brillouin wrote this equation in 1923, and you see in his case, R goes down to 0. But R is now kind of acting like a parameter. ds squared is this one, R goes down to 0. What do you find? These two are equivalent. And they're equivalent to Schwarzschild's. Because when Schwarzschild's little r equals 0, that's the same as when Droster's little r is equal to alpha, and the same as when Brillouin's little r is equal to 0. They all come out the same, and they produce the radius being 0. What the cosmologists want to do, they want to take Drosta's solution where alpha is less than or equal to r and make r go down to naught. Why? Because they think it's the radius. We've already seen that it's not so. And they want to make the r equals naught the origin of their geometry, but that's not so. Let's have a look at the Schwarzschild ground form. This is something that I wrote down in about 2005, in my first paper on this subject. Have a look at this equation, particularly RC. Now we see here, n is any positive real number, and r is any real number. So is r naught, any real number. R naught and n are only arbitrary constants. You can pick what you like. But notice something. When r equals r sub 0, the radius that I calculated before is always naught, and is independent of the value of n and r naught. Completely independent. That's what you want, independence of coordinates. So you see that RC is equal to alpha, and RP of r sub 0 is equal to 0 for all values of r naught and all values of n. Let's take some examples. If I set r naught equals naught and n equals 3, and I take r greater than r naught like Schwarzschild did, we get Schwarzschild's solution. If I set n equals 1 and r naught equals alpha and r is greater than r naught, I get Drosta's solution. If I set n equals 1 and r naught equals naught, I get r, and we take r in greater than r naught, I get Brillouin's solution. These equations are equivalent. It's saying the same thing with just some different symbols, but they're exactly the same geometrically. So the question is, can Drosta's solution be extended down to naught to get Hilbert's solution and generate a black hole? Now we talk about metric extensions. Now, I'm going to show you here, if you couldn't see that you can't do that, let's take a specific example. Let r naught equal 0 in that equation for RC, and let n equal 2. What do we get? This expression, and RC is equal to r squared plus alpha squared, and you take the square root of that. Well, r squared is r is a real number, and you square the real number, you get another real number. But the difference is, this squared real number is always greater than or equal to naught. Can r squared take minus alpha? Can r squared be minus alpha? It cannot. Now, since this expression generates Schwarzschild's solution, Drosta's solution, Brillouin's solution, any number of solutions you like, and they're all equivalent, if any one of that infinite equivalence class can be extendable to make Hilbert's black hole, in other words, to make Drosta's solution go down to naught, then every single one of them must be on account of equivalence. Alternatively, or conversely, if any one of those cannot be made to go down to RC equals naught, capital RC equals 0, then none can on account of equivalence. Well, if I make, you look at this one, can r squared take values of minus alpha and make RC sub 0 naught? It cannot. So we don't need homeomorphisms, we don't need diffeomorphisms, we don't need Hausdorff spaces, we don't need topological spaces. This completely ruins the black hole with its simple mathematics. You cannot, because it's an equivalence class. Now notice something also. If I make RC, r equal to r naught, RC is always alpha. That means the Gaussian curvature for any of those solutions is always this value, 1 over alpha squared, no matter what r naught I pick, no matter what n I pick. That's Schwarzschild's, Drosta's, Brillouin's, and all, but Hilbert's is not there. Why? Because it's a complete disconnection from this geometry. That means you can't get black holes anywhere, and it's from Hilbert's solution that the black hole was spawned. They talk about curvatures. They talk about the Kretschmann scalar. This is sometimes called the Riemann scalar curvature invariant. Well, in the case of Schwarzschild space-times, it's given by f. And you see here that f of r naught is equal to 12 over alpha to the 4th for all r naught and for all n. Why? Because it's an infinite equivalence class. Can you get 12 over 0? Can you make the denominator of f ever go down to naught? No. So their claim that they can get the denominator to go down to 0 is false. Let's look at what's called the acceleration invariant. This is a geometry, so we're going to talk about points, moving points. Well, Doty proved a long time ago, or showed a long time ago, that the expression for finding the radial geodesic acceleration of a point in any of these Schwarzschild spaces, which have no physical significance, as we've seen, is given by this expression. And now, if I put in my RC, which is valid for all of them because it's an equivalence class, an infinite equivalence class, when r approaches r naught, r sub c approaches alpha, and what does the radial acceleration do? It gets as big as you like. So that means this is the same for every one of them, no matter what r naught you pick, no matter what n you pick. Well, according to the cosmologists, now we're going to get an acceleration that's approaching infinity where there's no matter. They try to drive Drosta's solution down to r equals 0 by using these fanciful things called the Kruskal-Szekeres coordinates. I'm going to write it, I've written it here, the Kruskal-Szekeres coordinates line element or metric using RC, because that's the one that generates the infinite equivalence class. You can see that, can RC ever be 0? Never. So does this extend RC down to 0? No, it doesn't. So their extension is a fairy tale. It can't be done. Now this stops in the tracks all of that paraphernalia that they have with black holes. Now let's have a look at the four black holes. Well, we can generate these from Schwarzschild's one way or another. And the Schwarzschild's black hole is, or so alleged black hole, is charged, neutral, no rotation. The Rise and the Nordstrom is charged, no rotation. The Kerr-Newman is charged and rotating, and the Kerr-Newman black hole is charged and rotating. What's rotating? Well, a point or the circumference of a circle, according to them. Now, I'm not going to go through all of them. Here's the overall ground form. I wrote this long ago, but none of my critics have ever noticed it, of course. None of them understand it, of course, but it's really simple. When you see RC here, it's been generalized. All of black holes now the supposed black holes are contained in this expression by simply selecting the required parameters. Now, you will see here that R sub C of R naught is equal to sigma, where sigma now has charge, Q, which is squared, and angular momentum, A, which is squared, in the expression for sigma. But R sub C of R naught is equal to sigma for all R naught and all N, as it must. Can RC ever be 0? Well, you look at RC, no, it can never be 0. It can't take values less than sigma. Now, if I put in Q as naught and alpha as naught, sigma reduces exactly to alpha. That's the Schwarzschild one, without rotation, without charge. It's exactly what we need. So on account of this one being inextendable, none of them can be. So the black hole is a fallacy. It's nothing other than a generation of irrational imagination coupled with nonsensical mathematics that has no relation to physics, because Einstein's field equations R sub UV equals naught have no physical meaning. Here is an expression that I have obtained for the overall Gaussian curvature. Now we see that this is a very complicated expression. Now, what is a spherical surface? Well, according to the pure mathematicians, any surface which has a constant positive Gaussian curvature is a spherical surface. We look at this expression, it's not positive and constant. Why? Because that means it's not spherical. But if I put A equals 0 here, not alpha equals 0, A equals 0, the angular momentum, it reduces to a spherical surface. If I make Q equal 0 and A equal 0, it reduces to 1 over alpha squared. That's Schwarzschild's, the Gaussian curvature of the surface in Schwarzschild space-time. This expression covers them all. None of them permit a black hole to develop. Now here's a complicated expression for the overall Kretschmann scalar. Again, I use RC in its most general form, which is in the slide before, and we find that this one here is never 1 over infinity. Or so what they will say, 1 over a quantity that goes to 0. So I'll say that again. It will never have a denominator that can be 0. It's always a positive finite value. So their reliance upon the Kretschmann scalar for curvature going to infinity at the center of a black hole is complete and utter nonsense. Some of them like to confuse you even further by writing these equations in what are called isotropic coordinates. Well, here's an expression I developed long ago for the isotropic coordinate form. Now, you will see that in these two forms, they relate to spherical symmetry. This expression here, you see that it has a different form. You've got alpha over 4 to the n now. Why? Because isotropic coordinates, see the expression on the right-hand side of the part with the power of 4? That's nothing other than the expression for Euclidean 3 space. So if you rewrite it like this is what's called isotropic coordinates. That's all it means. Now I calculate the radius in isotropic coordinates. I get the radius is RC is this, and at R sub P of R sub 0, that radius equals 0. And it doesn't matter what value of R naught I pick, or it doesn't matter what value of N I pick. It's completely independent. And it generates an infinite equivalence class, none of which are extendable to a black hole. And on account of equivalence, you can't make any go down there to a black hole. Isotropic Schwarzschild Gaussian curvature. Well, I calculate that, I get exactly the same as with Schwarzschild's case. Because we're dealing here with isotropic Schwarzschild space-time. Well, if I put it in the ordinary form, we still get the very same Gaussian curvature, which we must. After all, they're equivalent. That's a different class, but it's still equivalent. The acceleration invariant. We saw the acceleration invariant. It has exactly the same properties. But they'll tell you that's where the event horizon is. But again, the acceleration goes off to infinity, where according to them, there's no matter. One thing that they've never calculated is Riemannian curvature, probably because it's too complicated for them. So I went to the trouble of doing it. It reinforces everything that I've said. How do you calculate Riemannian curvature? Well, you've got this thing here. On the numerator, we've got R sub ijkl. We recognize that as the Riemann tensor of the first kind. U and V, these are direction vectors. So if you take a point, you put two vectors on there, you can put them any direction you like. So you see that the curvature depends not only on position, but on the direction vectors that you attach there, right? In the case of a two-dimensional space, this reduces down to 1 over R squared in spherical symmetry, the one we had for Schwarzschild. Now, in non-spherical spaces, in spherical spaces, we still do the same. We still use this to calculate. Non-spherical spaces become really complicated, and I never bother with them because it's no point anyway. But it's too complicated to bother with. So how do we calculate it? Well, the U and V are direction vectors. We know what R is, and G. G is defined in terms of the components of the metric tensor as given there. I'm going to give a definition. I didn't make it up. The mathematicians did. I just borrow from them. I use what they tell us to use. I trust the mathematicians have done it right. Sometimes they don't. Anyway, definition. If the Riemannian curvature at any point is independent of direction vectors at that point, then the point is called an isotropic point. Why? It means it's the same everywhere. It's independent of the direction vectors. Here's my calculation for the Riemannian curvature of Schwarzschild space-time. Note, RC is still there. R is a real number. N is any positive real number. W we see is composed of two determinants. It's a product of two determinants which involve the direction vectors. The term on the right is very complicated, both numerator and denominator. So I've just given you the result. You can always go back and check it if you want to make sure that it's right. You might find a mistake somewhere. If you do, let me know. I do make mistakes. It's true. Everybody makes mistakes, so there's no shame in that. But correction is the important thing. Cosmologists make mistakes and they just say, oh, well, we'll go on. Riemannian curvature, the Schwarzschild invariant. Well, if I calculate the Riemannian curvature of Schwarzschild space-time, I get Ks. I'm going to put the S on it. Now we're talking about Riemannian curvature rather than Gaussian curvature. This Riemannian curvature applies to the whole 4 variables, whereas before we were talking about a surface with 2. Now I take the whole lot of this Schwarzschild space, my generalized form, which generates them all, and that includes Schwarzschilds, Droste, Brillouin, all of them. It's not Hilbert's, because his is not equivalent. And we get 1 over 2 alpha squared. This is finite and invariant. It's the same for every single choice of R naught and N. I can do the same for isotropic coordinates in Schwarzschild space-time, right? And with all of these more complicated expressions. Why? Because now we're in isotropic coordinates, we get a different expression for K sub S. And when I make the calculation, we get this. 1 over 2 alpha squared. Why? Well, it's Schwarzschild space. We've got to have the same curvatures, otherwise it wouldn't be an invariant. If you want to check these calculations, I've written a paper. It's 100 pages long, 60 pages of it's appendix in mathematics. 40 pages is quite readable to anybody who's not conversant with all of this mathematics or wants to learn it at least. You can go to this paper. It's an acknowledgement of sorts to Professor Gerardus Tuft, who gave me a very silver platter as an opportunity to reply to his criticisms. And so there it is. If you want to go there, all the ugly details are there in appendices. All the calculations you can go through and see how it's all obtained. Now, we're going to write Einstein's field equations now in a different form. Einstein wrote them as this. Before it was Ricci tensor equals 0. This is a different form. You see now it's in terms of the Riemann-Christoffel symbols. The left-hand side is geometry. The right-hand side, there's no sources. And the square root of the negative of the determinant is 1. Why? Because when you take the determinant of this metric For example, Schwarzschild's metric, you get -1, you get a negative number, so you have to multiply by -1 to get the square root of a positive number. And Einstein sets up this, what's called a unimodular situation. Cosmologists will throw at you, oh, this is unimodular coordinates. That's why he did it. So what? Now, Einstein makes a modification to the Riemann-Christoffel symbol because he puts a negative in front of it so he can write the top equation with a plus sign. You have to be careful. You can lose signs when you read Einstein. Okay. Now, according to Einstein, from that first equation that I gave you, he does a lot of mumbo-jumbo. He uses a Hamiltonian, and he gets up to this thing here. And he says on the left-hand side, we've got this partial derivative. It's really a divergence thing. And on the right-hand side, or it's a partial derivative thing at this stage. I'll talk about divergences shortly. And in the right-hand side, he says, since there's no matter here, right, and there's energy because the gravitational field has energy, I need energy. So what does he do? He concocts a thing called his pseudotensor. This is this little t with subscript sigma and subscript mu. And t is just a number that you obtain. It's an invariant that you obtain from t superscript sigma and subscript mu by setting sigma equal to mu, as we see down here. T is equal to t with sigma and in both subscript and superscript. It reduces the tensor by 2 values, right? And so a tensor with no superscripts and subscripts is a scalar or an invariant. And Einstein defines his pseudotensor, remembering this is what he uses to describe the energy of his gravitational field. Because even though there's no matter there, no mass, he wants energy because, according to him, matter is everything except his gravitational field. That's an important thing to remember with Einstein. Everything except his gravitational field is matter. Well, his gravitational field has energy. So he concocts this thing and says that's the energy. Then how does he get the material sources in? He simply adds it. He adds now the energy momentum tensor. See, now the little t has got a big T added to it. He took that equation and he expanded it by adding in the source. Now he says this describes his gravitational field with its sources. It doesn't look like the equations that we started before, but it's the same kind of thing, more complicated form. Now, here you find that there's a capital T. Well, this is obtained by contracting. When you set a superscript equal to a subscript in a tensor, you perform what's called a contraction. And in the case of a two-dimensional tensor or a two-valued tensor, you get a scalar because it reduces by 2. Well, there's one on the top and one on the bottom. Cancels out. Now you've got a scalar. So you see he's got the energy momentum tensor and the scalar that results from it. And he says now the right-hand side is the energy of the gravitational field and its momentum and the material sources of the gravitational field as well and its energy. Then his energy equation is this. The total energy of his gravitational field is the sources plus the field itself. The total energy is this in a closed system. Now notice, the thing about T is that it's not a tensor. It's a pseudotensor. It's not a tensor. So you cannot take tensor operations when you add it to a tensor. The big T is a tensor. The little one's not. So he cannot take a tensor divergence. So he has to take an ordinary divergence. So when you take an ordinary divergence, he gets 0. He says, voila, we now have conservation. Well, first, there's some problems here. It's not a tensor divergence, it's an ordinary divergence, and you need the tensor divergence to go to 0 to formulate a conservation law in theory, in mathematical form. But he can't do that. I'll tell you why. Look at this. We're going to look at some symbol salads. The top one is a word salad. Do you recognize it? Maybe it's Dutch. Maybe it's double Dutch. You know what? It's nothing. Why? It looks like a sentence. It smells like a sentence. It's got a nice European thing there so I expanded a little bit with a naught with double dots on it. It's got a full stop and a capital letter and a comma. And it looks like words, but it's drivel. Well, that's word salad, right? And then you look at the one below it. You think, oh, that's marvelous. Einstein wrote that. It's marvelous. You know what? It's just as much mathematical salad as the one before it is word salad. You know, but you can't see that, can you? I'm going to prove it to you. Metrics of zero class is a theorem. I didn't make it up. Go and see the mathematicians. Metrics of zero class of any number of variables n are characterized by the necessary and sufficient condition that their Riemann-Christoffel curvature tensor vanishes identically. Now, I've put a note. The Riemann-Christoffel curvature tensor for Einstein space-time does not vanish identically. So we're in this thing. Differential invariance. Theorem 2. Metrics phi of class 0 have no non-zero differential invariance. Metrics of non-zero class have no first-order differential invariance. The invariants greater than 1 are the invariants of phi, the Riemann-Christoffel curvature tensor, and its covariant derivatives. So we've got a definition, we've got a theorem 1 and 2. Now we contract Einstein's pseudotensor. He's treating it like a tensor, so we'll perform a tensor operation on this one, as he does, and we get t, just like he does. So the constant t, or the invariant t rather, has this form. We notice something about it. It's a function of what? The components of the metric tensor. In this time, it's written with superscripts. This is just another way. It's called a contravariant tensor. You can write it as contravariant above, covariant with them all below, or a mixed tensor with superscripts and subscripts. So we just switch them around. The delta thing, that's a Kronecker delta function. That's either 1 or 0. If the superscript is equal to the subscript, then the Kronecker delta gives 1, otherwise it's 0. But you see here, also remember that these Riemann-Christoffel symbols, these gamma things, we saw before that they're functions of the components of the metric tensor and their first derivatives. Well, that means Einstein's t here, his invariant, is a function of the components of the metric tensor and their first derivatives and nothing else. Well, we see by theorem 2 here, they don't exist. So by the method of reductio ad absurdum, we assume that Einstein's pseudotensor makes sense in mathematics. We apply a mathematical procedure to it by contracting it. It produces junk. What do we know about the premise? It's junk. So that means his conservation of energy is rubbish. He can't do that. It's nonsense. The whole thing is nonsense. The upshot of this is that Einstein's field equations must take this form. If they're going to have any form that's kind of like physics, right? And I use that very loosely because it isn't physics, but kind of like physics, it must take this form. So we see now on the left-hand side, we have the material sources. That's T. Notice that I've written it here in mixed form. Okay? There's a reason why I want to write it in mixed form, because I'm going to take a tensor divergence of it. And I want to write it in the way Einstein did. So you can go and check. Yes, he wrote it like this. Now, the first term now are the components of the energy of the gravitational field. The cosmological constant, that fudge factor, is stuck in there as well. And notice something. This here is also an energy equation because it's the sum of the energy momentum of the gravitational field and the energy momentum of the material sources. That's Einstein's E that he had before with his little t, his pseudotensor, and t. Now I can take a tensor divergence of it, which is what we really want to be consistent. We take a tensor divergence, which I've indicated by that little semicolon. I won't worry about how you do a covariant derivative in a tensor divergence. We don't want to know that. All we know is that when we take a tensor divergence of this expression, we get 0. Voila. We now have a conservation law. Trouble is, what are you conserving? Because if you look at the top equation, every closed system in this case, like in this form, has a total energy of 0. Does that match experiments? The closed system, the total energy and momentum of a closed system is always 0. That's nonsense. And so the whole theory is nonsense. This leads me now to some closing comments, a little bit of levity here. For all of those who are lost a little bit with the mathematics, we can have a little fun. I've come now to Riga. No, it's not the city Riga. It's for the Rusted Iron Gong Award for spectacular phantasmagoria and gross inanity. And the nominees are Gerardus Tuff, Professor of Physics, Nobel Laureate, Utrecht University, for this gem. When I spoke to him about this, he sent this to me in an email. I have the evidence, so if anybody wants it, I can give it to them. He says, of course, no astronomer in his right mind would claim that R stands for spatial distance. Well, you saw what he called it. He had 5, didn't he? He didn't know what he was talking about. He had 5 of them. 4, at least 4, I think 5. But in his notes on general relativity and his notes on black holes, on his own website, what does he say? where R0 is the smallest distance of the light ray to the central source. Isn't that a radius? Ordinary stars and planets contain matter. T sub UV does not equal naught. Yeah, material sources. With a certain radius, R greater than 2m. Here C and G is 1. He's using Hilbert's. So that for them, the validity of the Schwarzschild solution stops there. So despite the right-mindedness or the wrong-mindedness of astronomers and astrophysics, 't Hooft tells us that it's both the distance and a radius as well. And yet he's told us that nobody in their right mind would do that. I wonder what he was smoking at that time. Jos Bland Hawthorne, this is one of my favourites. This guy, he's a professor at the University of Sydney at the Institute for Big Questions. I'm serious. It's not a joke. I didn't make it up. The president is, I think, currently John Webb. He's well known to me, as anybody who's been to my webpage will know. Anyway, the University of New South Wales has this Institute of Big Questions. Bland Hawthorne is there, but he's at the University of Sydney and also the Institute of Astronomy there. He says this on National Australian Television. I know, I watched it and I downloaded it. Some objects are so massive that the escape speed is basically the speed of light and therefore not even light escapes. You know, the journalist sat there like a stunned mullet because he didn't even know what he said. But we know what he said. This is because he's saying that black hole event horizons, well, they have that schizophrenic property of having and not having an escape velocity at the same place. So he's a good candidate. Now we come to our old mate Hawking. He's ubiquitous. He's everywhere, this guy, you know. He's like a Big Bang himself. At the Big Bang itself, the universe is thought to have had zero size and to have been infinitely hot. Really? It's got no size and it's infinitely hot. Well, what carries the temperature, Steve? You know, don't you think you've got to have something that has a temperature? If you take a solid, what is it? Well, you've got these particles bumping around. You take a liquid, there's particles bumping around. You take a gas, there's particles bumping around. Well, we can go take a plasma, there are particles bumping around. But he's telling us that nothing can have a temperature. Not only that, it's infinite, really. An infinite temperature, that even doesn't even make sense. What can have an infinite temperature? Okay, we go, Clem Prikey, this guy's a good one. Clem Prikey, he's a bicep 2 scientist. You know all about bicep 2? You've heard of it. He's a physicist at the University of Minnesota. Now, these guys are the guys that said, we sampled the universe when we sampled B mode polarizations in the so-called cosmic microwave background when the universe was, after the universe it lived for only 1/1,000,000th of a trillionth of a trillionth of a second. Now, this is delusional science again. I wonder where they got their clocks. Probably at CERN, because that's where they make the Large Hadron Colliders. And our final one, good old Larry, God bless him. He's a professor at Arizona State University. I'm surprised he wasn't here today to give me a hard time. It seems quite plausible that our universe may be just one universe in what could be almost an infinite number of universes. Larry said that on National Australian Television. I know, I watched it, I downloaded it. Well, we asked Larry, just how close, Larry, did you get to infinite number? Really? You got to it's almost an infinite number. How close do you get? You know, you wonder where these guys went to school. I said it before, we're glad we didn't go there. And so who are the winners? Well, I couldn't decide, so it's a dead heat. They all get the prize, and finally, green grass and high tides. Thank you very much.